Uniform continuity is what happens on a set where you can use the same delta for every point in the domain. And as we've seen before, uniform continuity depends a lot on what the set you're talking about is. So for example, if your function is 1 over x, it looks like this. F of x equal 1 over x. So in this case, f is uniformly continuous on sets, I will say this informally, away from 0. Because near 0, it is not uniformly continuous, because near 0, the sort of the slopes become arbitrarily large, which ends up making the deltas become super small for those points. Uniformly continuous on sets away from 0, for example, f of x is uniformly continuous on, say, this set, 2 to 5, but it is not uniformly continuous on this set, say 0 to 1. You can't use a set including the number 0 because 0 is not part of the domain, but I can discuss that set, open interval from 0 to 1. The 1 isn't important, it's just the fact that it's open on the 0 side. It means the domain points, if you allow the domain points to include all the numbers, like really close to 0, then you got problems. It's not uniformly continuous. Okay, one thing that I said at the very end last time, which I said I wanted to talk in more detail about this time, is a theorem about if f is continuous, just the ordinary point-wise continuous, that is just continuous at every individual point, then it will automatically be uniformly continuous if you are using a compact set for the domain. So here's the theorem. If f is continuous on K, that is, K is a set, and K is compact, then f is continuous. Sorry, f is uniformly continuous. That's the point of this. On K. All right. So this is one way to tell if it's going to be uniformly continuous. If it's continuous on that set and the set happens to be compact, it is automatically uniformly continuous on that set. So for instance, right here, you could just immediately, this is immediately true because I know f of x is continuous. This 1 over x, it is continuous on the interval 2 to 5. And since the closed interval 2 to 5 is compact, automatically it is uniformly continuous. That's the compactness. All right. So I want to try and do the proof of this. As I said last time, the proof is not so difficult. And I think it's a good opportunity for us to refresh our memory about what compact means. And also a little something about continuity will come up that will be nice to refresh our memory before the test. I feel like I'm about to sneeze, but I don't think I will. It's disappointing. All right, so I think the best way to do this is by contradiction. So we assume that f is continuous. So let f be continuous on K. K is compact. And to get a contradiction, I'm going to assume that f is not uniformly continuous on K. All right. Not uniformly continuous, we can express that in terms of sequences. We were doing this in examples last time. Not uniformly continuous means you can have it's like you have two sequences, x's and y's, so that the x's and y's get close together, but when you plug them into the function, f of x and f of y's, they stay apart. So not uniformly continuous, this means, we did several examples of this last time, I know it was a while ago. There exist sequences xn and sequences yn, so these are two sequences of points in K. with the xn's and theyn's get closer together, so the way to write that is this: xn minus yn, absolute value goes to 0, but absolute value f of xn minus f of yn does not go to 0, and in fact you can say this is greater than some real number. I will call it, what am I going to call it? Call it whatever you want. But actually, we don't even need to say specifically on my paper. I just said bounded away from 0. So this f of xn minus f of yn, that does not approach 0. Can you hear that in the background? My kids are like throwing pots and pans around. So xn minus yn, that goes to 0, but when I plug into the function, it does not go to 0. It stays far away from 0. Okay? All right. What are we going to do with the compactness? I hope you remember the definition of compact. It means if you have a sequence of points in K, then it has a subsequence which converges to a point of K. That's what compact means. Any sequence in the set has a convergent subsequence, and it's the subsequence converges to another point in the set. So we can use that right here because we have xn and yn are in K. I'm going to say since K is compact and xn is in K, this means that there is a convergent subsequence. So I'm going to say there exists x nk. That's how we write a subsequence, right? And this converges. I'll just say it converges to x, where x is in K. All right? So because K is compact, any sequence in K has a convergent subsequence, and that subsequence converges to a point in K. All right? So since K is compact and the xn is in K, it means this. Same goes for theyn's, right? It means also that there exists some ynk subsequence converging not to x, but converges to some point y, where y is in K. Actually, you can say something about x and y. Since xn and yn, they must go towards each other, right? This thing here, xn minus yn, converges to 0. That means whatever xn converges to, yn must converge to the same thing. So actually, these two different values, x and y, I wrote them as different, but in fact, they are the same. So since xn minus yn, this distance goes to 0, it means the terms of xn, whatever they converge to, it has to be the same as whatever theyn's converge to, and that is x and y. So this means x equals y. These two sequences, they converge to the same thing, right? The subsequences do. The original sequences might not converge, but they have subsequences which converge, and those things, they have to converge to the same thing because the x's and the y's are getting close together. All right, what does this mean? Then I can say, just do the f of the subsequence, f of xn k minus f of yn k. Sorry, not equals, but this must go to 0. This is because xnk and ynk converge to x, and x is in K, so f is continuous at x. All right? We are trying to show that f is uniformly continuous. So you can't assume that it's uniformly continuous, but we can assume that it is continuous at every individual point of K. And since xn and yn converge to x, and f is continuous at that point, it means that this thing goes to 0. This is the sequential form of continuity, that when you plug, continuity means that if you have a sequence which converges to something, then f of the sequence converges to the same thing. All right. But this is a contradiction. You can see here, it's not quite on the screen because it's behind my head, but we said before, fxn minus fyn is bounded away from 0. But we just demonstrated that this subsequence, those subsequences actually converge to 0. That's a contradiction. You cannot have up here all of the terms are far away from each other. That's what this bounded away from 0 means. This is all of the terms are bounded away from 0, but down here we said that the ones that are in the subsequence actually go to 0, and those are in contradiction with one another. So can I just do this? This is the contradiction. All right. The contradiction was with the assumption that f is not uniformly continuous, so we conclude that f is uniformly continuous. We use the compactness. The old sequences converging inside K. All right. Are there any thoughts about this or questions? I meant to do this at the end last time, but we ran out of time. All right. Oh, was that a question?
K is 0 to 10, close to close. So does it mean that the function will be continuous uniformly continuous during, let's assume, 4 to 8 open intervals?
I think I can't hear so well, but you said if we assume that K is something like the interval 0 to 10,
Yeah.
f is, so it means that f will be uniformly continuous on, say, 0 to 10.
Yeah.
And then, did you ask, like, what about a smaller interval then?
Yeah, like open interval inside or...
Yeah. So it is a fact, and this is not hard to see at all from the definition of uniform continuity. Can I just say if f is uniformly continuous on A and B is a subset of A, then f is uniformly continuous on B. This is a true fact. Is that what you're getting at? Yeah. Okay. Good. Yeah, and in this, it doesn't matter if B is a closed set or compact set or anything. B can be an open interval as long as it's inside of a compact set, a compact subset of the domain. Then it will be uniformly continuous. Yeah, it's true. That's a good question. The reason this is true is just because the definition of uniform continuity. It has a bunch of stuff in it, right? The only reference to A, the set A, is when it says something like for all x, y in A. Some other stuff is true. So if you make this set smaller, if it's already true for every x and y in A, it will automatically be true for every x, y in B. And so the definition still works exactly. All right, great. Thank you for the question. Okay, so we have been talking like vaguely. I mean, before we talked about uniform continuity, we discussed the extreme value theorem. That is the fact that functions have a minimum and a maximum value. Continuous functions do. There's one more value theorem that I want to talk about for now, at least. And anyone remember? I was gonna poll the audience. Anybody remember another value theorem? I gave it away by writing the first letter. From calculus. There are two others that I know of that are something value theorem.
Is it the intermediate value theorem?
The intermediate value theorem, yeah. That's what I want to talk about. Do you happen to remember what the intermediate value theorem says? It's all right if you don't. Anybody remember what the intermediate value theorem is about? No, I'll tell you. The intermediate value theorem is about sort of intermediate, in-between values of a function. So it says, I'll just write it down as a theorem. It says let f be, it's only true for continuous functions, and it is about closed intervals. Let f be a continuous function on a closed interval with f of a less than c less than f of b, or f of b less than c less than f of a. Sorry, in our book, does it matter? Not really, but I might as well write the same. In our book, they don't use c in this position for some reason. They use L here, big L. So the picture you should have in mind is I have a function on a closed interval from a to b, and it's continuous, of course, and its values, you know, it does something like that maybe. So here's f of a, here's f of b, and then L is just some, you should think of L as like a y value. It's a number in between f of a and f of b. So it's, you know, maybe like here is L on the picture. All right. Then, anyone remember this? Can anyone remember the conclusion of the intermediate value theorem?
I think it's just that there has to be a value in between it.
There has to be a value. Yeah, something like that. Can you say more? What do you mean by there has to be a value?
Since it's continuous and it's between a and b, then the limit has to be between the functions of a and b. Oh. Something like that.
Something like that, yeah. Can anybody say it more specifically? Like this part is what's assumed in the theorem. So we assume that there is a L in between f of a and f of b. And then the conclusion has to do with some value down here. Any thoughts? It basically says that L itself is also a value of the function. Like L has some x value down here that it comes from. And that's what our book calls C. So then the conclusion is there exists C, a real number, with C in between A and B, and f of C equals L. All right. This is what the intermediate value theorem says. So the basic idea is if you have some y value, which is in between the function values, then that y value, in fact, is also one of the values of the functions. That L is equal to f of c for some other point c. And that other point c is in between. It's called the intermediate value theorem. It's all about if you have some y value which is in between, it does in fact correspond to some x value which is in between these other two y values. All right. One particular case of this, which is useful all the time. One in particular, what this means is if you have, say, a and b, and the function is negative at a but positive at b, it means that there must be some place where it goes through 0, right? So this, you could say, is a corollary. If f of a is less than 0, which is less than f of b, that means f of a is negative and f of b is positive, then there exists some c with f of c equals 0. If you have something which is negative on one end of the interval and positive on the other end of the interval, then it must have been 0 at some point in between, in the middle of the interval, right? This is a consequence of the intermediate value theorem. This is a special case where you use L equaling 0, and then you write all the same stuff. Okay. I would like to think about, as we have done in the past, I want to think about this closed interval here. To what extent does this have to be a closed interval? And what is really important about that set? Is it just the fact that it's a closed set? Or does it really have to be an interval? Or does it have to be, like, the closed interval a to b is compact? Maybe this is still true for any compact set. That's the kind of thing I would like to think about. In fact, in this case, the issue is not compactness. This case, I would say the issue is more about points existing which lie in between other points. All right, here from A to B, or from f of A to f of B. The statement is kind of saying, like, no matter which point you choose in between, it actually comes from an in-between point down here. These notions of points, like all the in-between points are inside of this set or whatever, that is what we call connected. We haven't talked about connected sets in a little while, but that's what's important about these sets here. This set AB, the interval A to B, it doesn't matter really that it's a closed interval. It matters that it's connected. And another way to say this, so the fancier way to say this is that fancy version, f of the closed interval AB is connected. That means when I plug the entire interval in to the function f, the resulting set is still connected, which means it still includes all of its in-between points. If you think it through, this, what I said right here about connected sets, is equivalent to all of this. All right, so this is what I want to try to demonstrate as our sort of theorem. This is a fancy version of the intermediate value theorem, and it just says that if f is continuous, then and we plug a connected set into it, and E is connected, then f of E is connected. And I thought it might be nice to go through this one because, just as a little review about connectedness, since we haven't talked about connectedness in a little while. If you begin with a connected set, that is, it includes all the in-between points, you plug it into the function, the resulting set is still connected. This is how you get the intermediate value theorem, but in a more sophisticated way. It's about connected sets, all right? I want to go through the proof of this one because, like I said, connectedness is something we haven't talked about in a hot minute. So we should refresh our memories a little bit. So let's see if we can do this. The conclusion here is that f of E is connected. So I'm going to say let f be continuous. And this is going to be by contradiction also. And E be connected. But to get a contradiction, for the sake of contradiction, I'm going to assume f of E is not connected. This is good, actually. If you recall, the definition of connected is, it's easier to say what not connected means than it is to say what connected means. And do you remember? This is something you should remember by the end of the week. But if you have forgotten, what does it mean to be not connected? Not connected means you can break it into two separate sets. We usually call them A and B, in such a way that the intersections are empty if you do A closure intersect B or A intersect B closure. I hope that you have that in your memory somewhere. We assume f of E is not connected, so we have sets f of E can be written as a union A union B, where A bar intersect B is empty and A intersect B bar is empty. All right, this is what it means to be disconnected. It means you can write the whole set as a union B, where these things are true. Closure of A intersect B is empty. A intersect closure of B is empty. All right, what this means, if you could try and represent this on a picture, you have your set E down here, right? And then the function, it does some stuff here. And then f of E would be, according to this picture, this stuff here, right? All of this. Sorry, it's under my beautiful head. All right. E is a connected set in the domain, and you do the function to it. Now, if it really is a continuous function, then f of E should also be connected. That's what the theorem says. But in order to obtain a contradiction, we have assumed that f of E is disconnected. So what that means is f of E somehow you can break it into two pieces, and it has like a gap in it. All right, where these pieces are A and B. Okay. This is not truly possible with a continuous function, but that's what we're trying to show. So the situation we are in right now is that we are somehow able to break f of E into two separate pieces, which they don't intersect each other. Even if you take the closure of one of them, it does not touch the other one. All right. Now, we want to somehow get a contradiction out of this. Let me just tell you the idea first, and then we'll write down the details. The idea is you take B here, and you pull out all the points which went into B, and then you also take A here, and you pull out all the points which went into A. All right? And if those two things are disconnected, that's a contradiction, because E is supposed to be connected. So this is the idea. We consider all the points which go into B. We also consider all the points which go into A. And then if you look at those two things, the fact that A and B are disconnected means that those two blue sets I drew will also be disconnected, and that's the contradiction, because E is supposed to be connected. Anyway, let's see, how can we write that sort of in detail here? I am going to, I want to call these sets C and D, and I'll name it so that that one's C and that one is D. So I'm going to say let C be, well, in set theory we would write it this way: E intersect F inverse of A. F inverse of A is called the pre-image of A. It's all the points from the domain which go into A. And I did E intersect because I only want the ones which are actually part of E. I don't want, maybe there's some other point like over here where its Y value is in A, but I don't care about that. I only care about the points inside E. So what is this? Just to write in more detail what that is, it's all the points X which are in E such that F of X is in A, right? That's what I'm talking about here. All the points in E so that when you do the function to them, you end up in A. And then D is the same, but with a B in place of A. So D is going to be E intersect F inverse of B, which is all X in E such that F of X is in B, right? These are my sets. Okay. Now, just because of the way this is all set up, we will automatically have, so I'm going to say since F of E equals A union B, we will have E equals C union D. If you think about it, C is all the points in E that go into A, and D is all the points in E which go into B. If you take those two things together, that should cover all of E, because all the values of E are in either A or B. And so if you look at C and D together, you get all the values of E. So we will have E equals C union D. But then to get the contradiction, we're going to show that actually this is a separation of E. Remember, the homework used this word separation. It means these two sets have that intersection property with the closures. All right, we will have E equals C union D. but I'll just say, but E is supposed to be connected. So C union D cannot be a separation, or else that would be a contradiction. So we can assume, I'll just say without loss of generality, it means that one of those intersections is actually not empty. Either C bar intersect D is not empty, or C intersect D bar is not empty. So I'm going to assume C bar intersect D is not empty. All right. Because E is connected, C and D cannot separate into two separate pieces. So those intersections, I guess they're not empty, right? If those intersections are always empty, then it is a separation. So C bar intersect D is not the empty set. So let's say that means that there is actually a point X in C bar intersect D. All right, what does that mean? So X is in C bar and X is in D, right? X is in D means, remember the definition of D is here. It means f of x is in B. All right, what does x in C bar means? This means that it doesn't mean f of x is in A, because that's what C is. It's C bar. What it means is x is a limit point. Well, it means f of x is a limit point of A, right? X being in C means that f of x is in C, but C bar is the closure, which includes all the limit points. So it means f of x is a limit point of A. This is where we use the fact that f is continuous to move from the limit points of C to the limit points of A. This requires f being continuous. Getting texts. Sorry about that. Important texts from my wife. Okay, anyway, f of x is a limit point of A and f of x is in B. This means, of course, f of x is in A bar. And this is the contradiction. So we said f of x is in B, right? And f of x is in A bar. So f of x, black please, f of x is in A bar intersect B. And this is a contradiction with our assumption before that A bar intersect B is empty, right? This is because f of, we assumed at the very beginning of the proof, these guys here, that these were empty. But we just found a point which is in A bar intersect B. All right. So I don't know if you can follow the idea all the way to the execution of the proof. The basic idea is you start with some separation up here, and you show how that automatically implies some kind of separation down here. That was the contradiction. All right. This is the fancy version of the intermediate value theorem. This is all about connected sets, and this statement about connected sets you can use to easily show the intermediate value theorem. All right. We got about 12 minutes remaining. I wanted to do two cute examples of using the intermediate value theorem to demonstrate some interesting consequences. Using the intermediate value theorem. So here are two quick applications, you might say. Not exactly applications to your own everyday life, but applications of the intermediate value theorem. Here's the first one. I'll write this as a theorem. The square root of 2 exists. This is an interesting fact, obviously. Everybody loves the square root of 2. I don't know if you've ever taken the time to wonder, is there even such a number as the square root of 2? I mean, your calculator can do it, so you probably feel like, yeah, there is such a number. But it's not entirely obvious that there is a square root of 2, unless you're already familiar with this from the rest of your life. Let me just say, this is the slogan version of this. What I mean by this, more specifically, I'll say i.e., there exists some number, I'll call it C in R, such that C squared equals 2, right? That's what I'm saying here when I say the square root of 2 exists. What I mean is there's a real number so that when you square it, you get 2, all right? Now, apart from the fact that you have like a square root button on your calculator, this is not an easy thing to prove. There exists some number so that such that C squared equals 2. How could you prove this abstractly? It's not obvious, to me at least. In fact, a good way to do it is using the intermediate value theorem. You can use the intermediate value theorem to show that lots of roots of things actually exist. Of course, you can't do the square root of everything, like the square root of -1 does not exist. At least it's not a real number. So there is something special about the 2 here. Let's just see if we can do this. We're going to use the intermediate value theorem. The intermediate value theorem concerns a function, right? You always use a specific function to use the intermediate value theorem. So you have to cook up a function. I'm going to use this function here. And you'll see why I chose that function in just a moment. Maybe you expected me to use the square root function, but the whole point of this application is to demonstrate that the square root is a real thing. So I think it's kind of cheating to use the square root function as part of your proof here. The whole point of this is demonstrating why you should believe that the square root is a real thing at all. Anyway, let's use this as my function. And I'm going to use that bit about the intermediate value theorem about if one value is positive and one value is negative, then there must be 0 somewhere in between. That's the simple version of the intermediate value theorem that I'm going to use. Then, for example, what happens if we plug some numbers in here? What is f of 0? It would be 0 squared minus 2 is -2. So f of 0 is negative. It means this function, whatever it is, when I plug in 0, I get a negative number. I would like to also plug some other number to get a positive. Can anyone say what x value can I use to get a positive answer? Who? What did you say? 2. I think he said 2. This is what everybody was thinking, I hope. If I plug in 2 here, I get 2 squared minus 2. That's 4 minus 2, which is 2, right? So when I plug in 2, I get something over there, all right? And that means, because of the intermediate value theorem, so just to write it very specifically, f of 0 less than 0 less than f of 2. And of course, f is continuous. That's because it's a polynomial, and we know that polynomials are continuous. We talked about that, I don't know, some time ago. So by the intermediate value theorem, the conclusion is there exists C in the interval, or C in the real numbers, with C in between 0 and 2, such that f of C equals 0, right? The intermediate value theorem is if I have a negative somewhere and a positive somewhere else, then there must be one in between where it's 0. And on this picture, in fact, I know the graph of x squared minus 2 looks like a parabola, right? And the actual C in this picture is somewhere around there. It's not at 1. It's like a little bit more than 1 if my picture is accurate. All right. But what does it mean that f of c equals 0? This means just plugging into the function f of x is x squared minus 2. So when I see f of c equals 0, it is c squared minus 2. So c squared equals 2, which is what we wanted, right? That was the whole point of this. I was trying to find some number such that c squared equals 2. And there it is. It is guaranteed by the intermediate value theorem. This does not give you any clue of how you could actually compute that number. It doesn't tell you what the number is, but it does tell you that that number must exist. All right? Excellent. Now, we all know you can compute it using your calculator or something, but the intermediate value theorem is not a constructive theorem. That is, it doesn't tell you what the thing is. It just tells you that the thing must exist. All right? Any questions about that guy? All right, I got one for you guys to try. I know we only have 5 minutes left, but it's very similar, and this is actually a comprehensive exam question from 2019. So this is the 2019 comp. This was, if you care, number 22, part C. It says, prove that there exists C, a real number, C between 0 and 1, such that e to the c equals 2. All right, it should go very much like what I just said. See if you can make it happen. This one I think is pretty easy in context, although on the comprehensive exam they don't tell you to use the intermediate value theorem. If you weren't expecting that, you might have forgotten that that's what you're supposed to do here. But anyway, see if you can do it using the intermediate value theorem. I'll give you, my clock says 2:45 right now. I'll wait until 2:47 and then we can talk about it. I'll give you 3 minutes. 2:48. Go for it. All right, it's 2:48. I hope that you worked this out. Really, it goes very, very similar to the previous example. Did anybody start off? You need to begin by creating a function. Can somebody shout out? What function did you use? Nobody wants to say it.
I use e to the x minus 2.
E to the x minus 2 is a great idea. Basically, you want a function which will be 0 at the point that you're looking for, because the intermediate value theorem is most conveniently expressed when talking about the value 0. E to the x minus 2. Excellent. Then you need to choose some value which is negative, some value which is positive. But in fact, in this example, because they said you need the c to be in that particular range from 0 to 1, you better use the numbers 0 and 1. So I have to check f of 0. This is e to the 0 minus 2, which is 1 minus 2, which is negative 1. And then f of 1 is e to the 1 minus 2. What is that? I don't know offhand the digits of e, but e is greater than 2. It's 2.7 something something, I believe. Anyway, this is greater than 0, whatever that is, because e is more than 2. On the comprehensive exam, you are allowed to use a calculator, although it's not very helpful. It's almost never helpful in the real analysis section. This may be one time when you want to verify that e to the power 1 really is more than 2, but it is. E to the power 1 is more than 2. So I have one value for which it's negative. Of course, this is minus 0, right? So that means f of 0 less than 0 less than f of 1. And so there exists c. C is between 0 and 1 with f of c equals 0, which means e to the c minus 2 equals 0, which means e to the c equals 2. I hope that's what you all said. And that now is the end of our time. So tomorrow we're not going to do any more new stuff tomorrow. We'll just talk about old stuff to get ready for the test. All right, see you all then.